Why is simulating quantum states so challenging? Have you ever wondered why simulating quantum states feels like trying to catch smoke with your bare hands? It turns out, the world of quantum mechanics is a lot stranger than we might expect. So, why is it so challenging to simulate these elusive quantum states? First off, quantum systems behave in ways that are completely different from the classical systems we are familiar with. At the heart of this challenge lies something called Hilbert space. This is a vast mathematical space where quantum states exist. As the number of particles or quantum bits increases, this space grows exponentially. Even a small number of quantum bits can representing an astronomical amount of information. This makes it nearly impossible for classical computers to store or process these states efficiently. Another hurdle is the way quantum mechanics works. Quantum states evolve over time in a linear fashion, but many physical phenomena we want to simulate involve nonlinear equations. This mismatch creates a challenge. To simulate realistic quantum behaviors, researchers often need to use clever approximations or hybrid methods. While quantum computers handle linear transformations well, they struggle with nonlinear dynamics. Then there is the fragile nature of quantum information. Quantum states are extremely sensitive to noise and decoherence. These are random disturbances from the environment that can cause quantum information to degrade or collapse. Current quantum devices, known as noisy intermediate-scale quantum machines, have limited numbers of quantum bits and imperfect control. This restricts simulations to smaller or simplified models instead of full-scale, realistic systems. Validating quantum simulations adds another layer of complexity. Classical computers cannot efficiently verify the results for large quantum systems. This means researchers must rely on indirect checks or simplified cases, which can introduce uncertainty about the accuracy of the simulations. Despite these challenges, quantum simulators hold great potential. They can explore phenomena that classical computers cannot simulate, such as real-time dynamics of particle collisions or conditions in the early universe. These simulators can bypass classical problems like the sign problem, which makes certain quantum calculations exponentially difficult for classical machines. The difficulty of simulating quantum states highlights how quantum reality defies our everyday intuition. The bizarre behavior of quantum particles, the explosion of possible states, and the fragile nature of quantum information all contribute to the quirky challenges of recreating quantum worlds inside a computer. This is why simulating quantum states remains a frontier filled with surprises, where even simplified models can reveal unexpected and fascinating quantum effects that classical physics cannot capture.